Next, we have Sudeep Bhatia. Hopefully I'm saying that right. The talk is titled Limitations to Optimal Search in Naturalistic Active Learning. Take it away.
Okay, wonderful. Hello, everyone. My name is Sudeep Bhatia. This is joint work with Lisheng He and Russell Ritchie. Everyone can see my screen, hear my voice? Okay, if the answer to that is no, I hope someone will interrupt me. Now, this talk is very similar to the previous two talks that we just had. Its focus, as in those talks, is on understanding how people explore through their minds, understanding how they're able to control this process of exploration, and maybe also characterizing the adaptive or maladaptive properties of these processes. What we're going to do, we're going to model specifically the memory search, the algorithmic memory search processes at play, and then we're also going to try and characterize mathematically how efficient or inefficient or how optimal or suboptimal the resulting search is. This is in some sense something that the last question of the previous talk alluded to. Now we're going to do all this in what I'm going to argue is a more naturalistic setting than what is typically studied in search and learning tasks. And our whole experiment is fairly complicated. So what I'll do is I'll start off this talk just by giving you an outline of our experiment. Hopefully that'll give you a feel for what it is that we're studying. Okay, so you're in our study. I give you this task, and what I've done in this task is I've assigned a continuous value, let's call it y, to common food items, to hundreds or thousands of foods in the world. Now, you don't know what these y values are, but you do know that similar foods have similar y values, similar properties. Okay. Your task is to ask me about the values of 20 food items of your choosing. You have to retrieve these 20 items out of your mind, one after the other, ask them to me. I'll tell you what their y values are. After that, there'll be a test phase in which I will present you with 20 new items, new food items, and you'll have to guess their y values, and you receive a payment based on how accurately you predict their y. Okay, so you start off this task, and maybe the first food item that comes to your mind is salmon, and you ask me, hey, what's the value of salmon? I say salmon has 7 y. Okay, maybe salmon makes you think about tuna, and so now you ask me about tuna, and I say tuna has 4, and then maybe your mind jumps to watermelon. You ask me about watermelon, and I say watermelon has 93. Now you do this 20 times, and then there's a test phase in which I ask you about food items that you haven't queried, let's say pizza, and you have to guess what the y value of pizza is, and you get paid again based on how accurate this guess is. Now, this is a property learning task. Y is a property that essentially the subject is trying to learn. It's a special type of property learning task. It involves active search. It's not passive. I don't tell you a bunch of food items. You have to ask me about the food items that you want to know about. It also involves naturalistic stimuli. That is, things that people encounter on a day-to-day basis. Food items, for example. There are hundreds, thousands of food items in the world. These are rich, complicated objects that people have a ton of background knowledge about. So they have to essentially use this background knowledge to ask me questions, right? And again, there's a vast query space because there are hundreds, thousands of food items that you can ask me about. And lastly, because there's vast query space of objects that people know about, what really this task also involves is search through memory. In many ways, a semantic memory search task. You have to retrieve items, different types of foods from your mind, and use them in your queries. Now, I would argue that such tasks are central to human cognition. They're rarely ever studied and almost never modeled computationally. Just to give an example, my daughter, who is 4 years old, is at a time in her life where she's trying to learn which foods are spicy or not spicy. So she regularly asks me, is this food spicy? Is that food spicy? Spiciness, in her case, is very much like the y value that my subjects are trying to learn. Okay. So these tasks are important. We want to model them. And we're going to model these behavior in this task using both algorithmic theories of human memory and theories of optimal search. In other words, we're going to specify this specify human behavior on multiple levels of Mars analysis, both on the algorithmic level and on the computational level. What I think makes this task interesting is that there is a tension between these two levels of analysis. Memory search is fundamentally similarity driven. Okay. as people retrieve items, those items queue other associated or similar items. This is a phenomena that we observe in several tasks, pre-recall from lists, reassociation, semantic memory search. People display semantic congruence. Optimal search, however, requires the opposite. In order to maximize information gain, you need to generate sequences of dissimilar items. Okay, just an example, right? If you recall salmon, we know from theories of human memory search that salmon will queue similar items like tuna. But of course, if salmon and tuna both have similar values of y, asking about both salmon and tuna doesn't really make sense. You want to follow a query like salmon with a query about a dissimilar item like watermelon or pizza. So there's a tension between what we know people do in memory search tasks and what really they should be doing if they want to behave optimally in our tasks. So we're going to explore this tension, if you will. We have several experiments. I'll just tell you about the experiments up front, and then I'll just present all the data one by one. Our main experiments 1A and 1B, involved around 200 subjects each. In experiment 1A, participants were given essentially the task that I just told you. They could search for around 1,500 different food items that we had compiled using WordNet and prior studies. So it would generate this mega list of around 1,500 food items. In experiment 1B, we had around 1,700 animals that people could search for. Again, similar task. We mapped these foods and animals onto Y using word vectors. Many of you, I'm sure, have heard of word vectors. They're obtained from techniques like latent semantic analysis, or more recently, techniques like word2vec or GLOVE. Intuitively, these are vector representations for words or concepts that preserve the structure of similarity between words and concepts. What we did was we took word vectors for all these thousands of foods or thousands of animals, and we mapped them onto 10 principal components and assigned Y values using random weights on those 10 principal components. So let's say we have food items. Here, there are just a handful of food items on 3 principal components. Similar food items are closer to each other in this space. What we do to assign them the property value that we're studying is we generate a random weight vector on these dimensions, and then with that random weight vector, we multiply the word vectors for these items to get the property value. So in study 1A, foods with the highest property value that was used in study 1A were apple, turnip, pawpaw, crabapple, and foods with the lowest Y value were skim milk, coconut milk, broth, cocktail sauce. Okay, we use different randomly generated weight vectors and therefore different sort of randomly generated property values in different experiments, but this is just one example. Okay, we have several models that we're going to use to understand human behavior in this task. So the most fundamental model is a model of memory search. We're going to assume that search through memory, that is our people's ability to retrieve different food items one after the other and ask the experimenter about those food items, is described using a first order Markov process, such that people transition between one item to another. And this transition, we assume, depends on 2 core variables: the similarity of these 2 items, which we're going to specify as cosine similarity of their word vectors, and the word frequency of the item that is being transitioned to. Okay, these parameters, beta 1 and beta 2, are going to basically characterize the degree to which human search relies on semantic similarity and word frequency. If beta 1 is really positive, for example, we know that people are transitioning between items in a way that is positively dependent on the similarity of these items. That is, they're transitioning from one item to another similar item. If beta 1 is negative, we know that they're transitioning in a way that is negatively dependent on similarity. So they're going to transition from one item to a dissimilar item. Okay? Intuitively, optimal search requires negative beta 1 values. What we know about human memory search, well, based on that, we can predict that people will have positive beta 1 values. Okay, we're going to fit beta 1 and beta 2 to our search data to determine whether these values are positive or negative. Okay, this model will basically predict how do people transition between items. Let's say they've generated tuna, they've generated salmon, then they transition to tuna, and transition to watermelon. That model will describe that process. Our second model is a model of how good people's search sets are. And for this, we're going to use a metric known as Bayesian d-optimality. And I'm not going to go into too many technical details, but it's basically a metric that quantifies if I'm trying to find these latent weight vectors how good is my particular search sequence for doing that? All right. So if I search for salmon, tuna, watermelon, how good is that sequence for determining what the weights on these three dimensions might be, what the property value might be? Okay. The last model we have is an ideal Bayesian learning model. This basically says that given what people have searched, given that they've searched for tuna, salmon, watermelon, found out the property values of those items, what is their prediction for, let's say, a new item, let's say like pizza, going to be? And the ideal Bayesian learning model says that basically people take what they know and they use it in an optimal manner, at least optimal according to Bayesian statistics. Okay, so these are three models that we're going to use in all of our tasks, in experiment 1A and 1B, and also in experiments 2 and 3. Now, experiments 2 and 3 are just like experiment 1A. We're giving people this property that they have to learn about by asking questions about foods. What we're going to do is, however, we're going to assign half the subject to a condition. So half the subjects get the same experiment as 1A. The other half get essentially a pure semantic memory search task. Basically, they don't have to learn any property. They just have to remember foods, list 20 food items that come to their mind. Experiment 3 is, again, like experiment 1A in the sense that half the subjects get that condition. The other half get coached learning. Essentially, the other half are told that in order to do well at this task, they must generate dissimilar items to essentially learn the property value efficiently. Okay, we're going to see whether these conditions vary in our subjects. Okay, we pre-registered experiments 2 and 3. Okay, so what did we find? Well, first thing that we found was these beta 1 values are all positive in all our experiments and for vast majority of our subjects. Okay, what does this tell us? This tells us that people are searching in a manner that is positively related to semantic similarity. They're transitioning between items that are similar to each other. If beta 1 was negative, right, we'd be getting the opposite pattern. But we're getting a positive beta 1 consistent with what we know about research on memory search, but inconsistent with what an optimal search model would specify here. This graph shows that a little bit more carefully. All right, on each point in this graph is a subject. All right, the x-axis tells us their best fit beta 1 value, the best fit essentially parameter on semantic similarity as inferred from their search sequences. The y-axis gives us the de-optimality of their search set, like how good of a query sequence did they generate. And you see a very, very clean, very strong negative relationship. People who generate optimal search sets, good search sets, do not search in a manner that depends positively on semantic similarity between foods, the small values of beta 1. Conversely, people who display a lot of semantic congruence, people who transition between similar items, they tend to have inefficient search sets. Another thing that we found, by the way, I didn't mention it earlier, but we also found a positive value on beta 2, that is, people tend to search for high frequency items, so food items that are mentioned more frequently in natural language. I mean, again, this isn't surprising. This is consistent with a lot of what we know about memory search. Okay, let's see. What does this graph tell us? Well, I don't have too much time, so I won't get into too much detail. But what we essentially see here is that if we take our Bayesian learning model, or Bayesian ideal learning model, apply it to the query sets that people generate, we can use that model to predict test performance. In other words, individual differences in query optimality map into individual differences in test performance. If you generate a search sequence that is similarity driven, that has low Bayesian de-optimality, well, if an ideal Bayesian learner will have a hard time using that sequence to make predictions in the test phase. We also note here that the ideal learner does a little bit better than human subjects, most probably because human predictions are noisy and our Bayesian learning model doesn't really allow for that noise. Okay, this is a complicated graph. Let's see, I only have 1 or 2 minutes left, so I'll focus on a few things. In this general graph, what we're doing is we're evaluating different types of search strategies. So in red, we've got the actual search strategy. That's like, what people actually did. In blue, we've got the random search strategy. Let's say you just randomly, you generate items using a uniform sampling rule. In yellow, we've got a frequency-based search strategy. You generate items based on their frequency of use in natural language. Green is a semantic similarity-driven strategy, that is, you generate items that are semantically most similar to the previous item. And blue is a Bayesian de-optimality greedy strategy. So you generate items that maximize, at least in sort of myopic sense, the de-optimality of your search set. A few things that we can see here. Firstly, obviously a de-optimality greedy strategy generates query sets that are high in de-optimality. And if you can see this little green line here, a similarity-driven search strategy just does not generate good search sets. What we observe with human search strategies, that's the red line, it's about as good as random when it comes to the de-optimality of the search set. So this red line is right next to the blue line over here. Okay, and that pattern also plays out not only when we measure the de-optimality of the search set, but also when we take that Bayesian ideal learner and apply it to the search set. We see that the best performing model, this purple line, is this Bayesian de-optimality greedy strategy. Worst performing model is this green line. It's purely semantic similarity driven strategy, right? And human search strategy is actually doing about as good as random in the middle. All right. So people aren't, they're not terrible. I mean, they could be worse, I suppose, but they're not really doing all that well here. All right, so in experiment 2, we gave people this task, and we also gave people just a simple semantic memory search task, just like generate all the food items you can generate. We thought that people would be less sensitive to semantic congruence, would be more optimal in our task versus a pure semantic memory search task where there's no incentive to generate dissimilar items. That was our pre-registered hypothesis. This was violated. We found no differences in experiment 2 between semantic memory search and our main task. And likewise, in experiment 3, we thought that telling people how to search, essentially generate sequences of dissimilar items, we thought that would improve their search strategy, to improve test performance. That's what we pre-registered. Again, our hypotheses were violated. So again, what seems to be happening is people suck at searching, and we can't really make them better searchers by giving them instructions. Now, you may be thinking, people are bad at searching. Do they even understand this task? Do they even know what an efficient query sequence is? That's what we studied in experiment 4. We gave subjects a bunch of query sequences generated by prior subjects, and we asked them to evaluate which of these sequences was more efficient or less efficient for the task at hand. And we found that people could do this. So most participants were above chance accuracy. The model accuracy at doing this was 100%. So even though people can't instantiate optimal search from memory, they're in many ways driven by semantic similarity. They can't control their minds, right? They can still, if you give them explicit sequences to evaluate, they can still tell you that, hey, this is a really bad search sequence, and this is a really good search sequence. They understand what's good behavior in this task. Okay, so to conclude, associative memory impairs naturalistic active learning. People are much worse than optimal. Behavior seems to be unaffected by task instructions, incentives. However, people can recognize efficient search sequences when explicitly asked to do so. And I think what's really an important takeaway from this is that we can start, modeling naturalistic search tasks. I mean, obviously this isn't, a completely real-world search task, but it's far more realistic, far richer than what is typically studied in the active learning literature. Most search tasks, if you look at the literature, involve these abstracted objects defined on 2 or 3, pre-specified dimensions. They might be like perceptual objects. Here we're dealing with rich, complex concepts that are stored in mind, for which people have, a wealth of background knowledge. And we're studying how they use this background knowledge, how they control the retrieval processes to solve the task. I think that kind of approach is necessary if we're going to use cognitive science to actually improve real-world learning or behavior. Thank you for your attention. I think we have a few minutes for questions.
Yeah, thanks for that awesome talk. We have time for maybe 1 or 2 quick questions there.
It looks like there's one in the chat. So it says, thanks, cool task. When imagining how I would approach this task, I think I might start with 1 food item and then manipulate 1 feature at a time. So similarity might be high, but there will be a good reason for it, considering my memory and cognitive constraints. Have you tried to see if some subjects might be doing something like that?
Yeah, that's a really good point. So yeah, so there could be, much more nuance in the search strategy than what we've actually modeled with our Markov search model, which is really only sensitive to cosine similarity between the concepts or between the foods, um, and word frequency. So yeah, I think that's certainly possible. I mean, another possible search strategy could be that I have what's known as confirmatory search strategy or test positive search strategy, where I have a feeling that I know what this property value is, and then I basically ask questions to confirm that. So that's another possibility. There's a lot more nuance, a lot more richness in human search data than what we have actually modeled. I think this is something that others can do, and maybe we'll also try and pursue in follow-up work. So great question.
Awesome. Can we do one more question from the audience?
I think that was my question.
Okay.
It's kind of a similar question, but I wonder if people might be better searches, or if they do this where they sort of like hold one kind of principal component or dimension constant, and then maybe that compresses the search space in a way that's easier to kind of come up with dissimilarity along one dimension than along 10,000 huge dimensions. And that might be kind of non-optimal from a Bayesian perspective, but it might be a lot better at getting like partway there.
Yeah, no, absolutely. And obviously Bayesian optimality is a pretty high standard to hold a human subject to, for many reasons. I mean, one is obviously they have cognitive constraints. The other reason is that people aren't always given this kind of task. I mean, maybe the task that they're evolved to do, or that they're adapted to doing, is one in which there's an exploitation trade-off, right? So you're not just, as my daughter, for example, right, when she's trying to figure out what's spicy, things that are not spicy she might eat and then get some positive reward from that, and things that are spicy, if she eats them, she'll get a negative reward from that. So in our task, people are asking queries without getting any rewards, and that task creates this artificial, perhaps, pressure to ask extremely distinct queries. But if you're getting rewarded for your queries, then there's an incentive, once you find a rewarding cluster of objects, to stay there, and that is something that is well predicted by a semantic congruent memory search process. So I think the question that you're asking, really the issue that it's raising, is that our task may not be capturing the kind of task, the kind of behavior that people have to solve in the world, and maybe de-optimality and Bayesian optimality in our task is really not a good metric. So I don't disagree with that.
Thanks.
Awesome. Thank you so much.
Thank you.